Students, can you hear me? Hello. Hello. Am I audible?
Yes, ma'am. Yes.
Okay. Thank you. Okay. Hello everyone. Very good morning to all of you, and very good evening to Abhijit sir. So first, I would like to extend a warm welcome to our today's resource person, Mr. Abhijit Chavan, a dynamic, result-driven leader committed to delivering enterprise-wide solutions for financial organization on the behalf of Department of Computer Science, Vivekanand College, Kolhapur. So I welcome you, sir. I would also like to welcome the students, all the faculties member and research scholars, those are on Google Meet or on YouTube Live, to the session of machine learning. Sir, let me introduce our department. We have created VCK Machine Intelligence Group. Many students, alumni and research scholars are members of this group. They share their research projects, their research work with us, and it's our honor that you accepted our invitation to share your views. So thank you once again, sir. And now I would like to introduce our resource person, Abhijit Chavan, sir. So in his 20 plus years of experience, he have progressed through various roles, starting from the ground up to deliver change and transformation. His expertise encompasses all aspects of financial innovations, from developing tools for corporate treasury and capital markets to deploying process automation for securities and settlement systems. He has generated numerous success defining and delivering IT strategies, having data analytics and business intelligence to execute comprehensive projects. He is always in lookout to experiment new concepts and technologies, that is in machine learning or natural language processing, to better the product. Let me share something about his academics. He has been completed B Mechanical Engineering in 1993. Then he completed MBA in Savitribai Phule Pune University. He has completed Masters of Science in Artificial Intelligence. So he is highly professional, technical, seasoned, and has sound business and finance knowledge. He has been in finance industry for more than 15 years, and he has worked as different reputed financial companies at different levels as program manager and technical leader. Initially, he worked in HCC, that is Hindustan Construction Company. Then he joined as senior programmer analyst consultant in United Nations and Development Program. Then he worked in Desh Bank as VP Program Manager, and now he is working as Senior VP, that is Senior Technology Manager, Capital Markets and Corporate Treasury. So this is the brief introduction of our resource person. And now, without wasting time, I requested to Abhijit sir to continue his session. So once again, I welcome you, sir, and now you can start. Thank you, sir.
Yeah. Thanks a lot for the introduction and warm welcome. I would like to thank Dr. and Principal R.R. Kumbar. I would like to thank Dr. V.B. Wagmare, Head of Department. And also I would like to thank the organizing committee, Mr. I.K. Mujawar and Mrs. Rajashree Padil, for giving me an opportunity to speak to you all, to discuss and provide my opinions about machine learning, what I have learned, and I'm always learning, but what I have learned so far and what I have practiced so far. So let's start uh, by introducing myself. I know that Professor Rajashree has introduced me quite a bit, but my simplest introduction is I am Kolhapuri. Okay, so let me start with that, and I have a lot of pride in that. Right. I would like to share my presentation with you all, and let's begin our machine learning journey today. So let me share my screen. Yeah. Yeah, I think you can see my screen now, right? Okay. So first, before we start learning, right, I would like to start with a quote from the father of our nation, Mr. Mahatma Gandhi, right? The quote goes like this: live as if you were to die tomorrow. Learn as if you were to live forever. And this is a very, very inspiring quote for me, right? And I have always nurtured on this particular quote. The word learn is what we are going to learn as well, but it's on the other side of it. That is, the machine is going to learn from us. So let's begin this journey, right? So today's agenda, the agenda for today is the part one is basically going to talk about machine learning, the introduction of various algorithms of machine learning, what exactly are the basics of machine learning in terms of overfitting, underfitting, what exactly is cross-validation, and what exactly is a confusion matrix. So this is what we are going to cover as part of part one. Part two is a live demonstration. So I have got some snippets of a number of different code or software, and we will go through that software across each of the points that we are going to learn as part one. So let's understand what exactly is machine learning, right? And there is a very nice definition that has been provided by Tom Mitchell, and the book Machine Learning from Tom Mitchell is an excellent read, and I would recommend everybody to read that book. It's really nice. It covers lots of basics on machine learning, right? So reading this example from Tom Mitchell's book, right? And this is exactly what I'm kind of showcasing it to you all on the screen, right? So machine learning has got four different parameters as per his example. One is the task. So the first thing is that what is the task that we are trying to solve, right? Now the task that we are trying to solve can be anything. It can be like flagging emails that are spam emails. Okay, so that is the task at hand, right? Now, this task, it gets passed to a system, I would say, or an algorithm or a model, right? And the responsibility of that model is to tag that task, whether it is a spam email or whether it is a non-spam email, right? And the outcome is basically whether it is a spam email or a non-spam email. Now, how would a model or an algorithm or a system understand that, hey, this is a spam email or non-spam email? It has to have some kind of an input. And this input is nothing but the experiences in the real world, right? So, for example, let's say if I receive an email, right, and that email came from a specific domain, right? And that specific domain is asking me to provide my age, gender, my salary, my credit card, dues, so on and so forth. That domain is not supposed to ask those kind of questions, but it is still asking me that question, right? So I would treat that email as a spam email, right? So that is just one training instance, right, of the experience that you're going to provide to the algorithm or model or the system, right? You can have n number of such instances, right? Even you might have come across the emails, right, spam emails, and you might have said, hey, this is a spam email, right? You might have tagged it as a spam email. So these training instances, my instance, your instance, and there are a lot of people in the world who might have experienced similar cases, all their instances forms the experience. Experience is nothing but a training data set that we are going to feed into this model or algorithm. And we are going to train this model saying that, hey, if you come across a task, the task can be a prior task, the task can be the new task, then you're going to tag it as spam. Okay. Now the beauty of machine learning algorithms is it has to understand the new instances of the tasks, right? Because the hacker or whoever is providing this particular emails, they're not going to sit quiet. They're not going to have only 10 different types of emails that they're going to send you, but they are going to keep on inventing different avenues of sending you emails and getting some sensitive information from you or just disturbing you, right? It can be any case. But your model has to be built in such a fashion that it is going to generalize. And this word generalize here is very important. It is going to generalize. It is going to understand the new instances of the tasks that you have to classify. And it is going to tag them accordingly. And that is been identified as the performance, right? The performance of the model is that it identifies the emails, the spam, non-spam emails, no matter whether they're new tasks, right? The performance has to improve. And when this happens, then we call that as a machine learning algorithm or machine learning model or machine learning system. The machine learning algorithm, model, or a system learns over the time and tries to improve its performance by identifying newly coming tasks, right, with the acceptance criteria that we have, which is spam versus non-spam classification. So that is what machine learning is all about, right? And that is what Tom Mitchell is saying, that, hey, there has to be an improvement because the tasks are going to change as we go. So is the algorithm has to be intuitive enough to understand them and classify them. That being said, let's move further. Now, this slide is, as I said to you, that look, my simplest introduction is that I am from Kolhapur or Kolhapuri, right? And while I was growing up in Kolhapur, I don't know whether this what you can say statement is still true with you all youngsters, right? But when we were growing up in Kolhapur, we used to often say, not often, but sometimes we used to say, hey, Arun Firun Gangavesh, right? And I would like to, put this in a context. What exactly this means? This means that the start and the end is the same, right? The starting point and the end point of anything. It might be a conversation. It might be some kind of a task. It can be some kind of a thing, where you have the start point and the end point, which is the same, right? There is no improvement per se. You're basically saying, hey, I have put in so much effort in understanding a particular subject, but no matter what I do, the performance of my performance in this subject, right, or a course is the same. I don't know what to do. I don't know how to improve, right? All my efforts are kind of futile. So this very statement has got so much importance. If you see Tom Mitchell's definition, it talks about improvement, continuous improvement in understanding, continuous improvement in learning something, right? So that is what he talks about as a machine learning model or algorithm, right? So Iran Gangavesh is basically absurd in terms of machine learning, right? And we should move ahead of it. Now, how do we move ahead of it, right? So first thing is that in order to tackle any problem statement or task at hand, what we need is we have to define what is our goal, right? The goal is very important, right? In a number of different ways, right? So it is the objective that we would want to achieve. We can measure the performance of what exactly we want to do with what, so on and so forth, right? So here I have listed a spectrum of, different possibilities of how we can discard the whole statement of Irun Firun Gangavesh, right? Now, and all of these inputs basically are the inputs to the machine learning that will give us better results, that will give us, continuous improvement to our learning models. Okay, so goals. I would like to take an example here, right? And a classic example is cricket, and I would bring that example very often in my presentation today. So the problem statement that I'm going to discuss right now is about cricket, right? And let's assume, and I over the years I have lost touch of cricket, but let's say that Shubhaman Gill, I think that is the new player probably, who is basically joining the Indian squad, right? Let's say Shubhaman Gill is going to join the Indian squad, right? And we would want to classify or categorize Shubhaman Gill as to what kind of batsman he is and whether he can open the innings for India, right, in 50-over match or test or 20 overs, whatever the case may be, right? So we would want to tag this particular person. Now, what is that is required in order to tag this person? So the first and the foremost thing is we have a goal of tagging this person, but what else is required? We need data, a solid amount of data. And this is what differentiates machine learning from artificial intelligence, right? We human beings are the classic example of artificial intelligence. Why? Because with limited amount of data, we can generalize a lot of things. We can predict a lot of things. We don't have to be taught about each and everything, right, to take some decisions. But with very little knowledge, we can achieve greater heights or results or decisions. We can make powerful decisions. But with machine learning, you need a lot of data, tons and tons of data, so that it can comb or mine through this data to achieve some kind of results, right? So the data that we are going to think today for this top batsman who is going to join the Indian squad is going to be, let's say, number of innings that he has played, what is his batting average, what is the strike rate, how many 50s he has scored, how many hundreds he has scored, what is the bowler type that he likes to play against, what is the bowling speed that he usually tries or likes to face off with, what is the match format that he would basically has played, what is the team difficulty level, whether he has played against Australia and scored enough runs, right? What were the team rankings then, meaning what was the team ranking of Australia when he played against Australia, and what is the type of pitch that he can best perform on, right? So this is the data that we need for the machine learning, right? Now, the third thing is that what is the relationship between the data? That is so important from the machine learning perspective. And that's exactly what the algorithms look for. What is the relationship between data? How does one unit of data perform related or dependent upon the other known attributes or features, right, of the data? That is where the relations come into play, right? And that is what we do. We predict that how is this specific unit of data Y going to behave based on the variables or other data points such as X, right? So that is the relationship, right, we try to look at in terms of the predictive models. The fourth thing is the descriptive models, right? So how do you quantify a specific outcome of the unit of data, right, compared based on the dependent variables or based on the other data points? How do you quantify the relationship between the data points, right? And based on that quantification, how do you basically group those customers or group, for example, how do you group Shubhaman Gill, or how do you categorize, or what bucket you would put Shubhaman Gill into the list of top level batsmen across the world, right? So how do you want to quantify the relationship? The quantification might happen based on what is his score, what type of pitch he has played, what is the bowling speed he has faced against, so on and so forth, right? So that becomes the descriptive models that we look at, right? Then comes the decision models, right? So the relationship between all the elements of a decision, right? It can be the known data, it can be the forecasted results, so on and so forth, right? So how do these decision models come into play, right? And all of this is going to happen as part of the machine learning process, right? At the end, what do we need? We need to validate the machine learning models or algorithms. That is very important. How does the machine learning perform, right, on the outside world? It might perform at its best when you have training data set, right? But when you really implement that model on the outside or realistic data, then how does it perform, right? So that is very important from the machine learning algorithm model perspective, right? And ultimately the implementation of the data machine learning model, right? So if you consider all these spectrum of possibilities that we talked about, right, then your end is definitely going to be very different than your start, right? It is going to be, it is definitely going to improvise, right? Because you have considered so many different things, right? In terms of what you want to do, in terms of data, in terms of relationship, in terms of derivation of some relationships, so on and so forth, right? And then you can easily discard the old saying that goes, Irun Firun Gangavish. Okay. That being said, let's move further. And before I move further, right? So I hope you guys are understanding. I hope I'm not going that fast enough. I hope I'm going in a very simplistic manner, right? So that everybody can understand what I'm talking about, right? So can Rajashree, is that same understanding you have?
Yeah. Yes, you can continue.
Okay, perfect. Okay, so let's go further. Now, what exactly, meaning where does this machine learning start and where does it end, right? So I want to, off the bat, I would want to really discard the second statement in this sentence, that is, where does it end? It doesn't end anywhere. It's a continuous process. You have to continuously evaluate your algorithm, analyze what exactly are the errors related to that algorithm, analyze how the performance of that algorithm is. Then the whole circle starts again, right? Starting from the study the problem, you basically train the algorithm, you evaluate the solution, you analyze the errors, and it begins again, right? Now, let's assume that 10, 15 years back, right, we were building intelligent software, right? We were writing, may not be that good, machine learning algorithms, but we were writing a lot of software code, right, with different kinds of rules. You have if and else statements and a lot more statements that you can basically program in, right? And they can achieve good results. They can achieve good, what you can say, outcomes, I would say, right? But there is a limitation to it. If you take the example of spam, there can be a number of different ways how you might get a spam email, right? It might be hundreds and hundreds of ways that you can get an email. And you cannot write rules for all these different, what you can say, conditions. You cannot write all these different conditions to identify or to tag a particular email as if it is a spam or non-spam email, right? And that's where the machine learning algorithm comes into play. And we have just seen that, hey, yes, to a machine learning algorithm, if I provide a data, right, a data source, right, and if I train the model, that model is not only going to make better predictions, but it is also going to generalize, right? Generalize, and it is also going to try to identify or classify the spam versus non-spam email on a newly coming data. Now that newly coming data, it might not have seen before. It might be a complete unseen data, but still it is going to predict that, hey, yes, on classify, yes, that this is spam versus this is non-spam. Okay, so that is where basically machine learning starts. It starts with identification of a problem, right? But it never ends. It's a continuous process. The data keeps on changing, so does the experience to the system. The tasks keep on changing, right? And the machine learning algorithm has to be re-evaluated to see if there are any errors, to continuously improve that algorithm so that you get better results from the system, right? So what is it good for, right? So definitely it is good for very complex problems at hand, right? So you have, if you see behind the scenes of what each algorithm is based off, right? You have, it is based off linear regression, logistic regression. You have very complex equations that these algorithms are based on, right? So that is where it is good for. It is good for if you want to provide, right, a long list of rules, right, to just identify a specific problem, then that is it good for, right? We don't have to specify a long list of rules, right? Your algorithm should be able to catch those within few lines of code, right? Fluctuating environments. So what does it mean? So we human beings have a very good, adaptability, right? We have a very good adaptability. We can easily, base our decisions on whatever limited experience we have in order to take a better decision, right? So fluctuating environment. So machine learning can adapt to the new data. It should be able to adapt to the new data, right? So that's where it is good for, right? And then we talked about when you want to basically try to solve complex problems or try to mine large amounts of data and make some sense out of it, that is where machine learning would be good for, right? And if you see this slide, I have this example, and this is the right hand side of the figure, which shows pink and blue colors. That exactly is the outcome of one of my algorithms. So what exactly it is doing here is, this was a k-means algorithm, which is an unsupervised machine learning algorithm. And it is basically clustering the students, right? In, let's say in India, I would have taken the math grades of all the 8th, 9th, and 10th students, science, English, and also their standardized test scores, like let's say common entrance exam, right? Those test scores. And what I'm trying to derive here is that whether based on this, their academic results or their academic outcome, whether a particular student can get into the top tier colleges such as IITs or IIMs or not, right? So that's exactly what my project was, right? And this plot that it shows or is shown here exactly demarcates, two categories of students. One, those who can be admitted to the top tier colleges, and those that cannot be, admitted to the top tier colleges, right? So that is the beauty of machine learning algorithm, right? So that's how you can basically start with simple problems. You can identify the solutions for it and then keep running with them, identifying and continuously improving the algorithm or the model so that you have better results as per the definition from Tom Mitchell. Moving further, now the slide basically showcases, and I just tried to put a lot more information on this slide, right? But mainly there are three types of machine learning algorithms, right? So one is called as supervised learning. What is a supervised learning? So it is basically divided into two types. One is a classification, which is yes and no, and one is a regression. Now regression can be an equation, it can be a linear equation, or it can be a logistic function, right, which basically finds a dependent binary variable based on nominal, ordinal, or ratio kind of variables. So what is supervised learning? So supervised learning is that you basically provide input to the machine learning algorithm, right, telling that algorithm that this is the right data, right? So based on my earlier example, if I receive an email and that email came from a specific domain asking me all the sensitive information, and I have tagged that email as yes, right, it is a spam email, then that forms a training instance, and that is nothing but a learning instance for the machine learning algorithm, right? And that is where it is named as supervised learning, right? Now, supervised learning, there are not many algorithms here, and they basically provide really good outcomes as well, right? In terms of, so if we look at this, like k nearest neighbors, that is one of the algorithms. Support vector machines, decision trees, random forests, neural networks, perceptron, especially, right? So we are going to see all of these in the second part of my demonstration, but these are the algorithms which are tagged as a supervised learning algorithms, where we feed some information to it, we provide the labels to the data, labeling them that this is the correct data, or classifying that this is the spam email or non-spam email, right? That's where it is called as supervised learning, because you are teaching the algorithm what is correct versus what is wrong. Then the second categorization of machine learning algorithm is the unsupervised learning. Now, in case of unsupervised learning, what happens is that we basically form the clusters of data, right? So let's go back to our example, right? So the top tier batsmen across, let's say, Australia, right, or India, Pakistan, or England, all these cricketing countries, right, they might have top tier batsmen who basically open the innings for their teams, right? And if Shubman Gill is a top tier batsman and would want to open the innings for India, then he would be clustered, or he would be grouped with those people, with the top tier people of the cricketing world, right? So that's how the unsupervised learning plays out, right? It basically takes the new task, new instance, and see where exactly that new instance can be placed based on number of different variables, right? And we talked about those variables just before or earlier, which is basically how many innings they have played, right? What was the highest score that they have, how many 50s they have scored, how many centuries they have scored, what is the bowler type they have faced against, what is the bowling speed that they have played against. All those things factor in, and they help to cluster that information. Now, Shubman Gill might be, he has never opened any innings for any of the teams that he has played. Let's assume, right? But somehow he's improvising. He has joined the Indian team, let's assume, and he's improvising. Now he is basically playing two down, right? Now he's playing one down. So what is happening here? Here the data is changing. The statistics for Shubman Gill is kind of changing, right? So as the data is changing, as the statistics for Shubman Gill is changing, he would be pushed out of the cluster that was dealing that basically grouped the middle level batsmen, right? He will be pushed out of that group, and he will be slowly pushed towards the top tier batsmen who basically open the innings for a specific country, right? So that is the job of unsupervised learning. It basically takes the data in, has got the experience based on whatever training data sets it has, basically pushes or tries to group that data into different clusters. Now, what are the examples, right? What are the examples of unsupervised learning or clustering, right? So let's say I am a regular visitor at Amazon.com, right? And I basically go and try to buy something from Amazon site, right? And I have a specific taste, right? I basically go and purchase items worth X amount, right? X quantity, Y quantity, so on and so forth, right? So behind the scenes, Amazon is basically trying to cluster or trying to put me into a specific bucket of the customers, right? And based on those buckets, right, they will try to market things to me, right? They'll try to market things to me. Okay, for this particular group of people who basically go and try to buy this particular brand, right? Then they would basically try to market that brand to me on my, ongoing purchases from their site, or for my ongoing purchases from their site, right? So that's where you can have a different, utility of the unsupervised learning model. The third is the reinforcement learning model. What is reinforcement learning model? So let's take an example of a child, right? And the mommy is teaching that child, hey, this is a hot water, and never try to pour hot water on your hands or fingers. They'll burn it. At the same time, the mommy tells the child, hey, this is the cold water. If you want to wash the hands with the cold water, right, that's the way to go. They will not burn your hands, right? They will not penalize you as the hot water would. The child is smart. The child says, okay, fine, mommy, I totally got it. Now, in this example, the child is an agent. The hot water and the cold water are the real world examples, right? The burning of the hand is a penalty, right? and the non-burning process is an award, a reward or award, you can call it as, right? So the child says, okay, he starts the hot water tap and takes the hot water on the fingers, and they really burn very hard, right? Then the agent realizes, hey, this is the penalty, right? This is, my hands got burned because of the hot water, right? I will never ever try to touch that again. So the child has learned from it. The child has learned from the penalty that he or she has received, right? Now, on the other hand, the child puts the hand under cold water, and he or she doesn't feel anything, right? It's just normal water, and then they basically can wash his or her hands by the cold water, right? So that's kind of a reward, right? It's kind of a reward in my example. Now, the agent basically faces the real world examples. If he gets the reward or award, whatever you want to call it as, right? That is the path. That is the path that is established with that agent. It learns from it that this is the right way to do it, right? But the moment agent realizes or receives a penalty, then he or she realizes that that is the wrong path and I don't want to take that path again, right? So that is where reinforcement learning comes into play. Now, what is the examples of where can we use reinforcement learning? It's the robot navigation, right? So imagine a robot, it is just moving straight, right? And there is a wall in front of the robot, right? The robot goes and, what you can say, dashes on the wall, right? Immediately it realizes that, hey, it has already dashed on that wall, right? And this is, and gets penalized for that, right? And it realizes that this is not the way to go. I need to find some other path, right? And then it basically changes its direction and starts to move in some other direction, right? So this is where the reinforcement learning is kind of used. Classic examples can be, let's say, drone, right? You want to fly a drone. The drone gets reward as far as it doesn't go and dash or dashes on tree or any other roof, so on and so forth, right? So that's where you can keep the drone moving, right, in a open space, right, and not basically crashing onto something, right? So that is all about reinforcement learning. Now, the other categorization here is just, I've just kind of put it for the informational purposes, but these are the three main categories in which you can find the machine learning algorithms, right? Now, the other one is batch learning. So what happens with batch learning? It is the same kind of learning. The only difference is that here the information or the experience or the training instances that we are going to provide to the algorithm, right? That is going to be in a batch manner, right? So let's say by evening, 5 p.m., you would take your system down, you would basically inject new training instances into your algorithm, and you will restart the algorithm, and then the algorithm will start to tag or classify the information for you, right? So that is kind of a batch learning. Online learning is a little bit different than batch learning. In case of online learning, you don't have to stop the machine learning algorithm. You just continuously feed the experience or training instance or data to the algorithm, and it would take it right away, right? And then it would basically try to classify or do things for you. Instance-based learning, right? So instance-based learning, okay, as per the example that we took, right? Okay, so Rohit, I only know his name as Rohit, who is a very good batsman for India, right? So he is an opening batsman. He has got, let's say, 25 centuries. He might have got, let's say, 50-50s. He likes to play against the fast bowlers, right? He has performed excellent against A teams, right? Similarly, let's say Virat Kohli, he's done similar kind of a performance as Rohit has done, right? And now a new instance, which is Shubhaman Gill, in our example, has arrived, right? If the data points for Shubhaman Gill match or come very close to the data points, right, for Rohit or for Virat Kohli, then that new instance can be, tagged very close to those two data points for Rohit and Virat Kohli. You can easily group them, or cluster them, right? So basically, in case of instance-based learning, it basically the algorithm learns from the instances at hand, then generalizes that information that it has learned to tag the newly coming instance towards it. Okay, so that's what exactly is the instance-based learning is all about. Model-based learning, further to that, we basically create a model based on specific examples, right? And then the algorithm uses that model to make some predictions in the real world, right? So that's exactly what is model-based learning about, right? But this whole slide, I know that it's a little bit busy slide, but it provides you a good categorization of what different algorithms are, and it also kind of provides you information of what other categories are for machine learning algorithms, but they're a little bit different, and I have colored them differently here so that you can realize that, hey, the main categories are one with red, blue, and brown colors, but the other ones are kind of there for your information. So far so good. Any questions anybody has? Let me take some questions out here, as I need a little bit of break. But any questions anybody has? Any opinions, any ideas, or anybody who wants to discuss freely, please go ahead.
Hello.
Yes.
Sir, does machine learning comes in, it's related to artificial intelligence programs?
That's a nice question. I just briefly categorize to you, right? In my opinion, right, machine learning predominantly works on large amounts of data, right? You have to continuously feed that data to it, right? But artificial intelligence is like human beings, right? Like we learn based on specific instances, then we take that instance, generalize the information related to that instance, and then we try to learn the other information, right, and provide some kind of decisions based off those, right? So in case of artificial intelligence, the data that is supplied to the agent is very minimal, or it's minimal compared to the data that goes into machine learning. In machine learning, you have to basically provide wide array, wide experiences to the algorithm.
Yes, sir, got it. Thank you.
Yeah. And then if you see the masters that I completed, that is actually an interactive intelligence, but the interactive intelligence is not that widely used term into the market, right? That's where I have said as artificial/interactive intelligence. Interactive intelligence is basically a step forward from it, right? So I'll give you an example. Let's say you have a car, Tesla, right? And let's say you want to go to office in the morning. So you open Tesla, you sit in Tesla. The moment you sit in Tesla, right now, what do we have, right? So if you sit into BMWs or Mercedes-Benzes or any other luxury cars, the car automatically realizes that you have sat on it, right, or in it, and then it automatically adjusts your mirror positions, it starts the car for you, so on and so forth, right? But the futuristic car, which is based on the interactive intelligence, is basically going to go further. It is not only going to do these things what I mentioned to you, but it is going to say, hey, XYZ, it's 9 a.m. in the morning. I hope you would want to go to your office, right? Shall I take you there? The moment you say yes, it is going to load all the maps to the train station that you go to every day, right? It is going to go park the car, and then it is going to say, hey, you have reached your train station or destination. You can go and take your train to your office, right? So how does it do that, right? So it is going to basically predict things for you, right? It is going to learn of what exactly you do on a day-to-day basis, right? So it is going to basically keep watch on you in terms of your behavioral things, right? In terms of what exactly happens at that particular point in time, on that particular day of the week, right? So that is where the interactive intelligence comes into play. Now, the moment it asks you, hey, it's 9 a.m., I'm going to take you to, I hope you're going to go to the office, and you are basically interacting with the agent saying that yes, the moment it does that, it interacts back to you by loading all the maps to the train station, which you go on a day-to-day basis, right? And it is going to start this car for you and start going or heading in that direction. So it is interacting with the humans. So interactive intelligence basically comes into play when a machine agent or agent basically interacts, or machine interacts with humans, and humans interact with machines interact with machines, so on and so forth. So that is what about interactive intelligence. I don't want to go too deep into it because then we will lose the touch on machine learning, but yes, that is the answer for your question. Any other questions?
Hello.
Yeah.
Sir, as you mentioned about Tesla, okay, and you said the car automatically does its work and take you at your destination. But as per how it's gonna work in India, because in India there are not roads prepared for that car, or that kind of program which which on it runs.
Correct.
Example,
Yeah. So yes, how
we
it
don't
basically
have proper
adapt.
lanes, proper roads on India. So
Yeah, I
how
got your
it's
question. So this is the futuristic model, right? And this is yet to be implemented even in US, right? And India is far off from it. But what I'm trying to tell you is that the interactive intelligence is an interaction that would happen between a human and a machine, or machine to machine. That is the interaction that would happen, and that's what is all about interactive intelligence, right? And believe me, there will be cars in future where they will work on Indian roads as well, right? We are heading in that direction, I guess. Okay. Any other questions?
Yes, any question is there?
Okay. So let's move further, right? And let's understand some of the basics of machine learning, right? And I would like to start with the overfitting and underfitting of the data, right? So before we go there, there are a few important things that we would want to learn about the overfitting and underfitting, right? And let's start with variance, right? And I want you to think about variance from the target function perspective, right? It is the model, or it is the function that you are writing, right? And the amount that the estimate of this target function, right? And how this estimate of this target function will change in case if you change your training data. Or so, for example, let's say Let me take an example for you. Yeah. So I hope you can see my screen here, right? So let's say y is a function of x, right? Now, this particular function will give you some output, right? Will give you some output. But where x is my training data. Now, if I change this x to x1, right, how is my estimate going to change in terms of x1, right? That is what is called as variance, right? Now, if there is a significant change in the estimate, then it is called as high variance. If there is no change in the estimate, right, it is called as low variance. That's what it is called as, right? Now, the other point here is the bias, right? Now, the bias is nothing but what are the assumptions, right? Function easier to learn, right? So, for example, let's say if this function, right, you have created this function so that is easier, it is easier to learn, right? To learn the relationship or to learn the relationship between your input and output, so on and so forth, right? If you have created this function that is very easy to learn, right? But at the same time, right, it doesn't learn much based on the specifics of the data. This terminology is a little bit difficult to understand, right? Like you have created this function that is easier to learn, but because your function is easier, it is going to lose a lot on your specifics of the data points, right? Specifics of the data points. So that is very important, and I will show you how basically that is going to help you in identifying whether your algorithm is overfitting or underfitting, right? So now, more the assumptions, right? More the assumptions about the form of the target function. So the more the assumptions you make about this form of target function, that is called as a high bias, right? The less the assumptions you are going to make about this function, it is called as the low bias, okay? Low bias. Now, if we go back to this particular algorithm, right, and I would start with this here, right? If you see the right-hand plot, right, where I have an overfitting zone and an underfitting zone. Now, in case of overfitting zone, right, based on my description, that the estimate of the target function will change based on the training data, right? What it means is that the model that you have designed has gone so deep into understanding the specifics of the data that the curve or the function basically tightly fits with the data. And this is the plot that shows that it is overfitting the data. It has learned each and every minute point of your data that you have provided, right? And it has fit the curve to it, right? And it is basically overfitted. Now, what happens is that when it overfits, right, when your estimate changes, right, then what happens is that it basically does not generalize that better or good enough, you know, to identify the outcome of your outcome for your problem statement, right? So what it means is that your accuracy on your training data set can be very high, but the same accuracy on the real world problem will not be high because it is not able to generalize properly on the real data, or the worldly data, you can say, real data, right? So that is what is called as the overfitting of the model. Similarly, when you go on the other side of it, your variance basically goes down, right? So your estimate is basically, estimate of the target function doesn't change that much, right? That is also not a good story, right? Because that also is going to, what you can say, it is also not going to, the model is not going to generalize, right, the outcome of your machine learning algorithm, up to mark, right? And that's where your predictions are going to go down, even if there is a low variance. So what it means here is that you have to have a proper balance, right, of or proper trade-off between the bias and a proper trade-off between variance for your model to predict in a certain way or in a good fashion, right, where you have a better accuracy of all your outcomes, right? Now, I would like to go with the examples of high variance, right? So in case of high variance, where will you find high variance, right? So decision trees, right? These are non-linear machine learning algorithms, right? Where they are very flexible enough. When I say flexible enough, their estimates of the estimates of the target function or model would change based on the training data, right? So those are the models, like the algorithms, like decision trees or k nearest neighbors or support vector machines. Those are the examples where you can find high variance. The algorithms such as linear regression, logistic regression, those will have low variance, right? Because the estimate of the target function is not going to be that different based on the training data. And those are the low variance algorithms, right? Similarly, if you see the bias, the high bias algorithms, it's exactly the flip side of the high variance, right? So the algorithms such as linear regression or the logistic regression would have a high bias, right, on your data, whereas the algorithms such as decision trees, k nearest neighbors, basically would have a low bias, right? Now, what is a good fit, right? What is a good model? The good model is where the trade-off between the variance and the bias is optimal, right? And that has been shown here on the right side on the plot with a dotted line, right? That is where a good model or a good fit model can be achieved, where the error term is very less, right? Your variance is optimally placed, as well as the bias is optimally placed. Okay, so this is the good model. Now, as I said, your data here, basically the data here, the model basically fits exactly to your data. It causes generalization error, not able to predict in a good way or with a very accurate results in a real world scenarios, right? So this is the overfitting. This is good fit because if you see the line, it basically goes through or cuts through all the data points. Very good generalization. This model can generalize based on this data in a very good manner. Whereas underfit, this particular line, I don't know what that line is doing, right? It basically is not representative of any, it is not representative of many of the input data, input data points. So that is kind of underfitting model. So that is what about overfitting versus underfitting is. So any questions on this particular topic?
Hello. There is request from one of the student. Can you explain it with example? What is how we can select training data, how we can select testing and validation data?
Yeah, I'm coming to that example on the next slide. So I just want to cover one more point on the bias that we talked about, right? So bias is nothing but what we are saying is that it is the assumptions made by the model to make the target function easier to learn, right? So it is easier to learn in the way that basically they are when you say that it is easier to learn, meaning it is, what you can say, they are less flexible to learn, right? The flexibility is in the non-linear models, which is the decision tree models, so on and so forth, right? So in case of linear models or logistic regression models, they are less flexible to learn. They're less flexible to learn. And that is basically distinguishes between this non-linear and linear models, right? So the low bias models are basically the decision trees, which are very flexible, and the high bias models are basically the linear regression models, which are very less flexible. They generally are less flexible to work with. Okay, so that's the demarcation between the low bias and the high bias models. Any further questions on this?
Sir, how can we know that a model is a perfect fit? It is working as a good fit.
Excellent question. Hold your thought. I will definitely go through that during the second session, right, where we will go through some actually code snippets, right, and then I will cover that point, right. What is a good fit? There are lots of different things we can fine tune the model, and I'm definitely going to cover that during the second part.
Okay, sir.
Now, cross-validation. So what is cross-validation? Right. So that's what we're going to talk about right now. Right. So traditionally, what we do is we basically go with the holdout model, right, where we take a data set and then we kind of split that data set into a training data set, which is, let's say, 80%, and test data set, which is kind of 20%, right? And then we basically perform on that model, right, on this particular training data, test data. But is it a good strategy? Is it a good strategy? Probably not, right? So if you go and look at the definition here of variance, what do we say here? The amount that the estimate of the target function will change if different training data was used, right? So is the estimate of the target function going to change based on the different data sets, right? In case of high variance, that estimate is going to change, right? That estimate is going to change. Now here, the training data set is so what you can say is basically 80-20. It doesn't go through a number of different examples, right? It just basically cuts it through 80-20. You perform one training run, and then you perform one run on the test, and that's about it, right? That causes a very high variance, right? Because it has learned from very minimal training instances. So are you getting the point here? Like, it has basically only looked at 80% of the data, right? And that is your model. That model is not going to perform best on the real world example, right? because the estimate of that target function, which has learned on a very minimal data set, is likely to change when it is implemented on the real world scenarios, right? So what is the solution for that? So the solution is this, right? It is called as cross-validation. So you take the same data set, right? Let's say these are 100 rows, right? And you basically split that data into 80-20. So you have 80 rows of training data. Your first fold is 20%, which is your test data. So you basically train the model on this 80-20, right? Then on the second fold, in a k-fold model, on the second fold, what happens is that your training data slightly changes, right? Because your fold 1, which was the test in round 1, now becomes the training data set, whereas fold 2 becomes the test data set, right? So what is happening here is your model is trying to learn on lots and lots of samples of data. As against the holdout, what happened is that you basically trained your model from fold 2 to fold 5, you tested on fold 1, and that's about it. And then you basically implemented this model on a real world example, and that is not going to give you better results. But in this case, in k-fold model, what is happening is that you are basically running the model, right, on k-1 subsets of training data sets, right? And then you're basically training on a lot more data points compared to your holdout model, right? And your model is going to learn perfectly, and which is going to basically give you better results in terms of reduction in variance as against and bias, right? And that model would give a better prediction on the real world examples, right? Now, the third point is further improvement, I would say, to k-fold model, and that is called as a stratified k-fold model. Now, what is stratified k-fold model? So let's take this example. In case of this first round, where you have fold 1, fold 2, fold 3, fold 4, and fold 5, right? That data set has got different samples of data, okay? Different samples of data, right? So for example, it might have, let's take our example, right, of batsmen. Now, it might have middle order batsmen, it might have top tier batsmen, it might have the batsmen that come, at the tail end of the, order, so on and so forth, right? But in case of stratified k-fold, what it does is, if you take fold 2, it basically provides equal amount of samples of different examples. For example, the top tier batsman, the middle order batsman, and the tail end batsman, right? It basically samples that data and puts it into fold 2. Similarly, fold 3 will have similar sample. Fold 4 will have similar sample. Fold 5 will have similar sample. So it will have instances of top tier, middle level, as well as tail end batsmen into or embedded into it. And what it does is that gives a good, what it can say, generalization, or basically learning. I would not say generalization, but basically learning for the model or algorithm in question, right? By which it can generalize the real data, the real world data appropriately, right? And this also, in fact, helps us to reduce the variance, reduce the bias, and come up with an optimal model, that can perform better in the real world, right? So the ultimate goal here is how well the learner will generalize, right, on the unseen data, on the real world data, right? That is what is the ultimate goal here, and cross-validation would basically, try and help to reduce the variance, to take out the bias, right, and give a proper machine learning algorithm or model that can really perform good on the real world. examples. Any questions here?
Sir, can you explain bias with an example? Like
Yes,
what
yes, I will definitely explain you the bias, right? So what is a bias? Right? Let's take a simplistic example, and we don't have to go that deeper into the subject, right? But what I'm saying is here is that, let's say if you are building a function, right? And that function has got very complex set of data, right? Underlying data and the relationships within this data, right? But you are not basically giving a well thought to that particular data, the specifics of the data, and you came up with a target function, right? That is very easy to learn, right? Easy to learn, but it is not going to go into the specificity of your data points, right? Then what good is it going to do for you, right? Is it going to behave good? No, it is not going to behave good. It is always going to underperform, perform, right? Because ultimately you have to have a model or a function that would basically address all the relationships, the specificity of your data points in order to make it work in a proper way or proper fashion. Is that?
So it's like an error, simply.
Yeah, so look, on both the sides, if you see, this is the error curve here, right? It is the generalization error curve here, right? So on both the sides of the graph, right, you see that the error increases, right? You see error increases in case of high bias and in case of high variance. Both are not good, right? Your model has to be somewhere here where you have both in balanced way, right?
Yes, sir.
You have to place your model here.
Yes, sir.
And now let's take an example here, right? So let's say you were, and let's take the cricket example as well, right? So your coach, let's say you're taking coaching lessons from your coach XYZ, right? And your coach tells you that, hey, you have so how you want to treat a particular ball, right? So let's say the particular ball is at the chest level, right? And your coach tells you that, okay, when the bowler bowls, when it's a fast bowler, bowler bowls a ball which is at the height of your chest, right? Then your coach has told you to leave that ball, okay? Leave that ball, gone, right? And that's how the coaches earlier used to tell, right? If it is a chess height ball, just leave it. It's of no use, right? You might basically give a catch to some of the positions, and you might get out. There are lots of things that can go wrong with that kind of a ball, right? But if you see in the what I can say, if you see in the recent cricket, right? What happens? You give the bowler throws a ball at a chest level, and basically the bowler is basically going to slap it down for a six, in any different positions, across the ground, right? So now what has happened here is that if you would have listened to your coach, right, what would have happened? You would have not got any good result, right? Because the coach has told you not to do this, right? You are basically saying that, okay, fine, I'm not going to do this. Why? Because there might be any number of things that might happen with a chest level ball, right? But on the other side, the flip side of it, you have said, hey, I'm going to go for a six, right? And you have taken a chance and you have gone for a six. Both of them are extreme conditions, right? But you can easily basically duck that ball down and keep it on the pitch, right? You might not go for a six, you might not leave the ball, but duck it, take a single run, right? And probably that might be an optimal decision at that point in time, right? Because you are getting a run, there is a very less risk of getting catch or out, right? And not leaving the ball at all, right? So what the figure here or the plot here tells you is that you've got to be here in the middle or optimal in terms of variance and bias by which you will get better results from your model.
Yes, sir.
Sir, as you told in k-fold cross-validation, as the model will be multiple iterations over the same data. So will the model overfit as we are providing the same data multiple times?
It will not, right? So that's what we said, because if the data is, what happens in k-fold model is that in case of holdout model, you are only going to get chance to learn on 80% of your data, right? But if you take the k-fold model, you are basically going to, and the test data is completely out of it, right? Whatever is there on the test data is completely out of it. But in case of k-fold model, you are also learning on the test data. You are not left out any data point, right? That's what we saw here. So fold 1 was your test data, but in fold 2, but in the second iteration, fold 1 was training data. So you're basically learning on fold 1 also. As against the holdout model, you would not have learned anything on fold 1 data.
Yes, sir, but we are learning 5 times.
You are learning 5 times, yeah, on all different instances of the data.
So will it cause overfitting?
It will not cause overfitting. It will basically reduce your variance because it is going to provide an adaptability to the function, right? Because you have learned from a number of different instances of the data to generalize the outcome in the real world problems.
Yes, sir.
So variance, when would variance come into play, right? Variance would come into play when you have learned on less number of instances, right? When you are learning on less number of instances, there is a likely possibility that the estimate of your target function might change, right? It might change based on the real world problems, right? When I say change, it might change drastically. It might cause a high variance, right? Your estimate has to change, but that estimate changing has to be optimal, right? So that word optimal is very important here, right? This word optimal is very important here. It cannot change much, it cannot change less, right? It has to be optimal in order to get better results. And there are ways and means, as I said, we'll go through those ways and means how you want to do that, right? And some of the examples are here. You can use cross-validation to reduce that, as well as you can basically fine-tune your model with different hyperparameters and also get better results based on those as well. Any questions still, or you're good? Okay, so let's go with the last topic of part 1, which is the confusion matrix, right? And this is where we basically try to check the accuracy of the model, right? Now, the first example I would want to take is the recent crisis that we have, which is COVID-19 crisis, right? So as I pointed out on slide 2, right, what is important for us? The important thing is that what is the problem statement we are trying to solve, okay? Now, if the problem statement at hand is COVID-19, right, and if you have these results right in front of you on the left-hand side, right, so what exactly does it entail? So, let's say there is a patient, there are a number of patients, let's say there are 1,000 patients, and you have tested all the 1,000 patients, right? The actual, so there are 998 patients which were actually negative. They are not COVID-19 patients, and they were predicted as negative. Okay, they were predicted as negative. So what has happened here? The prediction is absolutely fabulous, right? 998 people have been predicted as negative, and they were actually negative. There was one person which was positive, and that has been predicted as positive. Perfect. The model has performed very well. But there was one person which is actually positive, but has been predicted as negative. Now, what has happened here? The accuracy of this model, if you see, is 99.9%. Now, will you say that this model is perfect? It is performing the best? What is your take on it?
No,
Why not?
because still it's 99%. There is 1% chance that it could be false.
The real answer is, what is the cost of your false negative, right? Here, this particular thing represents a false negative, right? So this particular person who is COVID-19 positive, and you have left him out from your model, right, by testing him or her as negative, that is a very contagious disease, and it can basically affect thousands of people, right? And it can also, kill hundreds of people, right?
Yes.
So the problem statement that you're trying to solve here has got a lot of risk. The cost is humongous, right? So in this case, though the accuracy of your model is 99.9%, right, it is not that accurate, right? Because the cost of false negative is too high in this case. Okay, so that being said, let's say what happens here, right? So let's go on the right hand side. On the right hand side, what we are doing here is we are basically to understand this whole model, what we are doing is that we are just tagging it by true negative, false positive, true positive. Okay, there are three important what you can say factors in testing the accuracy of a model. The first one is the precision, right? And the precision, what it deals with, and I just want, for the simplicity, I have kind of set a boundary in red and green for this precision versus recall, right? Just for the simplicity of our understanding. So what does precision do? The precision basically checks the true predicted positive results, right? Its denominator is true predicted positive, right? So the precision formula is nothing but it's true positive upon total predicted positive, right? But actually what it is doing here is, it is finding what is the cost of false positive, okay? False positive. What is the cost of false positive? So let's take the example of a spam, right? Versus email, spam, to detect whether the email is spam or non-spam, right? So you have received a email, right, which is basically negative, right? It's not spam, it's not non-spam, right? But you have predicted that it is a spam. What happens? That email directly goes into your spam folder. Okay. Now let's say that email was from a business, for a business proposal with a time sensitivity, and that model has sent it or tagged it as, hey, it's a spam, and it has sent it to your folder, right? What would happen? You might have problems with the business proposal that you are dealing with, right? So what is the cost of false positive here, right? That's what we are basically determining on the precision. Whereas the recall example I just talked about, the COVID-19, here we are determining the cost of false negative, right? Now what happens is that the third part for the accuracy is F1, and the formula is very simple: 2 times precision into recall upon precision plus recall, right? So what we are trying to do here is we are trying to minimize the cost of false positive and false negative. Now, if you minimize this particular cost of false positive and false negative, your denominator is going to be less, your numerator is going to be high. So your F1 score is going to be high. The higher the F1 score, the better is the accuracy of your model. Right? So that is where the accuracy to test a particular model comes into play. And with that, I think I will end the part 1. Any questions on this slide?
Student, anyone have the question they can ask?
Okay, so I think, Rajashree, I think we will start on part 2 in another 10-15 minutes, or can we do that?
Yes, you can start it after 10 minutes. So students, तुम्हाला काही क्वेश्चन्स असतील, डाऊट असतील तर विचारा. मी मगाशी ओळख करून देताना तुम्हाला मुद्दामच दिली नाही की शेवटी आपण सांगायचं की अभिजित सर कोल्हापूरचे आहेत आणि मराठी त्यांना उत्तमरित्या पण येते. तर तुम्हाला डाऊट विचारताना काही असं वाटत असेल की इंग्लिशमध्ये कसं विचारायचं किंवा काय, तर तुम्ही मराठीत विचारू शकता. फर्स्ट इयरची जी मुलं आहेत त्यांना थोडासा हा पार्ट नवीन आहे. सो तुम्हाला काही समजलं नसेल तर तुम्ही विचारू शकता. ओके, नेक्स्ट सेशन जो आहे तो प्रॅक्टिकल सेशन आहे. He is going to demonstrate practically what is machine learning, how we can work on data. So we will meet after 10 minutes. Is it okay, Abhijit?
Yeah, that's fine. 10 minutes
Yeah.
will be fine. I'm just going to stop sharing, and I'm going to put on mute, but I'm going to leave the things as it is, or as they are.
Okay. So students, we will meet after 10 minutes, okay? On the same link. So we will see after 10 minutes. Okay, thank you once again.